Last time all we did was to define a planar tangle. And this is an object in the plane which had 5 features. So I'll just remind you quickly: external and internal disks, then there were marked points on these disks, on the boundaries, and third was a collection of curves of 2 types, open and closed, or strings. And then there was distinguished regions or star regions, and lastly we had shading, a black and white shading. And the important thing about planar tangles is it's defined up to an orientation preserving diffeomorphism of R2. Okay. So now I want to use these tangles to define this object known as a planar algebra. So let's give it a name. So say P is the planar algebra. First of all, there's some data and some axioms for this. So let me describe the data associated to a planar algebra. So the data associated to the planar algebra, there are 2 kinds. First is vector spaces. So one vector space pk epsilon for every color k epsilon. And recall that the set of colors is just this cross plus minus 1. So for every color you are given one vector space denoted pk epsilon, and then there are maps. Given any tangle, and let us suppose that this tangle has color k0 epsilon 0 and internal disks of colors k1 epsilon 1 up through kb epsilon b. So given such a tangle is supposed to give you a map of vector spaces with domain and range as follows. This specifies a linear map. Okay, I didn't say vector spaces over what? One vector space pk epsilon over some fixed field, typically complex numbers. So mostly we'll be interested in complex numbers, but you can do it over other fields as well. And given any tangle of this kind, this is to specify a linear map denoted by ZTP. This T is for the tangle, P equals this tangle, and this P stands for the name of the planar algebra. And where does this map go? This goes from a tensor product of vector spaces of these vector spaces, k1 epsilon 1 up to kb epsilon b to k naught epsilon 0. That's it. That's the data of a planar algebra. For every tangle you have a map, and for every color you have a vector space, and if a tangle is of this kind, then the map goes from this tensor product of these vector spaces to that. So that's the data. And then there are the axioms. So there are 3 axioms. So one is called compatibility with renumbering. Next is compatibility with substitution. And the third is the non-degeneracy axiom. So I'll explain each one of these in detail. So let's begin with the simplest one. Simplest one is compatibility with renumbering. So recall what renumbering means for a tangle. If you have a tangle which has internal disks, B of them, you could take any element of the symmetric group and get a new tangle by just renumbering the disks according to the permutation specified by the symmetric group element. So what this compatibility with renumbering says is the following. So suppose that T is that tangle over there, which is a one of color k naught epsilon naught and internal k1 epsilon 1 through kb epsilon b. So let T be such a tangle and take an element of the symmetric group. Then we know that we have a new tangle called sigma T. Consider sigma T. And the way we define sigma T, which as a subset of R2 is the same as T, except that it's which way does it go? Except that it's sigma ith disk is the ith disk of T. So you just renumber the disks of T by this permutation of 1 to b, which acts on these things. Okay, so consider this tangle sigma T. Now, the axioms of a planar algebra for T will give you one such map, and for sigma T will give you another such map, and this renumbering compatibility asserts some compatibility between these two maps. Then the following diagram is to commute. And what is this diagram? So let's first take k1 epsilon 1, kb epsilon b, k naught epsilon naught. You have such a map which is zt. Now sometimes as the planar algebra is understood, we won't write the p on top. Zt means for the planar algebra p. So we have this map zt. And on the other hand, you have another map. So what is the first disk of sigma T? So I want to put in here the other tangle sigma T. So what is the first disk of sigma T? The first disk of sigma T is the sigma inverse 1th disk of T. So here you will have P k sigma inverse 1 epsilon sigma inverse 1 tensor P k sigma inverse b epsilon sigma inverse b. So the function for sigma T will go from the tensor product of the vector spaces for the first disk, for the second disk, so on. The first disk of sigma T is the sigma inverse first disk of T, because the sigma 1th disk is the first disk of T. So you have this map, what is the compatibility between this map here and this map there? So what we notice, of course, is that these vector spaces that occur here and these vector spaces that occur here are just permuted versions of each other. So it's the same vector spaces except arranged in a different order. And so you have a natural map here, U sigma, where U sigma, if I take of some x1 tensor xb, it's just x sigma inverse 1, x sigma inverse b. So this diagram is to commute. This is formally, this is how one says it, but it's much easier to understand what this says informally. So what does this mean? What does this renumbering mean? So let's do this with one example. Say T is my favorite example, the multiplication tangle of 2 plus. And what is this? It looks like this. So here's the multiplication tangle of 2 plus. So let's call that tangle T. And we know that sigma T, if sigma is, so the sigma can belong to the symmetric group on two things, 1 and 2. So if sigma is 1, 2, the non-trivial element of that symmetric group, then we already saw that sigma of T, same picture, except that 1 and 2 are, the labeling of 1 and 2 interchanged. Everything else remains the same except for the labeling of 1 and 2. So we saw that this was sigma T. This is by definition sigma T. Now what this is saying is the following. What is the function associated to T? That is ZT goes from P2 plus, this is for D1, tensor P2 plus for D2 to P2 plus for D0. And for sigma T, this goes from P2 plus, this is for D1 of sigma T. So let me say D1 of T, D2 of T, and D0 of T. So D1 of sigma T, P2 plus D2 of sigma T to P2 plus, which is D0 of sigma T. But as we know, the only difference between sigma T and T is the way the disks are labeled. So D1 of T is the same as D2 of sigma T, and D2 of T is the same as D1 of sigma T. And so here if I put in this map U sigma, which just takes this here and this there by definition, this diagram is supposed to commute. Okay, but still what does it mean? What it means is the following. What it means is that if you consider this tangle T without labeling the internal disk. So consider a tangle T without labeling internal disks. So consider T, consider any tangle T. That is, you forget that labeling. Without labeling or numbering the internal disks. So if for example for that multiplication tangle, you just consider this, but don't label, don't number the insides. you consider everything else, all the other data is there. I haven't labeled. Then what you do is you give some input here and some input here, and these inputs should come from the correct place. So you put inside this an x in P2 plus, and into this you put a y in P2 minus. So once you give these inputs, so given
P2 plus.
Sorry, both are P2 plus. Yeah. So given appropriate inputs, the output is unambiguous. What does that mean? What that means is the following. So in this tangle, if I put x, if I give input x to this D1 and input y to D2, I will get some output. In this tangle, if I give input x to D2 and y to D1, I will get some other, possibly some other output, but this renumbering compatibility says it is not something different. Once you put in x here and y here, put in x here and y here, the outputs are the same. It does not depend on how you have labeled it, it only depends on the picture of the tangle and which input goes where. That is what it means. But to state it formally, you need to say it this way. Okay, so that is the first thing, first axiom. So the next axiom is compatibility under substitution. It is a little harder to state carefully. So for this we need to take two tangles, one of which can be substituted into some box, some disk of the other. So let T be a tangle as usual like this, and let T twiddle be another tangle, everything with twiddles. Including the B, right? The B is also twiddled. You have a new number of internal disks. So given tangles T and T tilde like this, let us suppose that the color of the ith disk of T, which is Ki epsilon I, is equal to the color of the external disk of T twiddle, which is K0 twiddle epsilon 0 twiddle. So then we know that then the tangle T circle T twiddle, where you put in T twiddle into the ith disk of T, makes sense. So now we have three tangles. We have a T, we have a T twiddle, and we have this composed tangle T circle T twiddle over the ith disk of T. And this is the compatibility under substitution axiom relates the function that is associated to T twiddle, and to this third one in a particular way. So what it says is the following. So it's what it says is actually the obvious thing, but we will write it out. So let us begin with let us begin with this one. So K1 epsilon 1 Ki minus 1 epsilon I minus 1. So remember how the disks of this are numbered. The disks of this are numbered as follows. First the I minus 1 disks of T, then all the disks of T twiddle in order, and then the rest of the disks of T. So the vector spaces I'll write in that order. So these are the first I minus 1 disks of T. Then we have all of T twiddle, which is P of K1 twiddle epsilon twiddle up through P of K twiddle B twiddle. Then I have the rest of the disks of T except the ith one. The ith one has been replaced by this. So I have to begin with Ki plus 1 epsilon I plus 1 up through Kb epsilon B. So these are the vector spaces corresponding to the internal disks of this in order. First disks up to I minus 1 disk, then all the disks of T twiddle, then the rest of the disks of T. And this function goes to the external disk of that tangle. The external disk of this is the same as the external disk of this T, which is P K0 epsilon 0 color. So it goes here. Okay, so that's one leg of the diagram. Then we have something else that we can do. What we can do is we can take this one and we could apply Z T twiddle to an element there. So what we could do is apply identity on all of these, Z T twiddle on that part, and identity on the rest. And let's see where that goes. Where does that go? So where that goes is, first you will have on the identity part, it goes to this. So this part is just the identity, that's just this first part. Now the second part, when I applied Z T twiddle, it will go into P of the external disk of T twiddle, which is P of K0 twiddle epsilon 0 twiddle, which is the same as P of Ki epsilon I, because we said that those colors were the same. And then these rest again go to themselves by identity. Ki plus 1 epsilon I plus 1 up through Kb epsilon B. Now of course if you read this, what do you have? K1 epsilon 1, Ki minus 1 epsilon I minus 1, Ki epsilon I, Ki plus 1 epsilon I up through Kb epsilon B. So what you can apply here is Zt. And that is again going to land in P of K0 epsilon 0. This diagram must commute. So suppose this, then this tangle makes sense, and we assume that this is the axiom. The above diagram commutes. So I want to make a couple of remarks about this. So what is this saying? So let's just do a simple example. So for example, suppose you have something like this. So here is a tangle. All colors are 2 plus. So let's say D1, D2 and D3. So here's a tangle. Now what the substitution axiom says is the following. Now in this tangle, what we could do is, we could, for example, let me just take out this part, right? If I take out that part, then I can write this as a composite of two tangles. So this tangle is a composite of two tangles. And what are these two tangles? T equals, let's say, that's D1 and D2. Now this is also a sum tangle, right? So this is sum tangle, and inside D2 what I am putting in is T twiddle, which looks like this, some other tangle. And I'll call this D1 and this D2 here. If that's T and that's T twiddle, then this is T circle T twiddle in D2. Okay. Now what this substitution axiom is saying is the following. What does this tangle do for you? This tangle basically will take some 3 inputs and give you an output. So where are these 3 inputs coming from? This is coming from a P2 plus, this is coming from P2 plus, this is coming from P2 plus, and the output there are goes into P3 plus. So this gives you a map from P2 plus, tensor P2 plus, tensor P2 plus to P3 plus. Okay, so it takes, if I give an x into this one, a y into this, and a z into this, then I get something in P3 plus which depends on this x, y and z coming from P2 plus. On the other hand, I could do this. What I could do is, I could give into this, I could substitute a y, and into this I could substitute a z. So when I substitute a y and z in this, the output of T twiddle will be something, say u, in P3 plus. This itself is a tangle, so if I substitute y in this and z in this, the output is going to be something in P3 plus. Then what I could do is I could take x here and substitute that u, whatever the result came, I could substitute that into this one and then see what happens. And then the assertion is that whatever you get by substituting x, y, z here, and whatever you get by substituting x here and u here, where u is given by this rule, they are the same. That's what the substitution axiom says. It's a very natural thing to assume, right? Substitution, both substitution and renumbering are very natural axioms to assume. You just think of a tangle as some kind of a machine which has inputs and outputs, and you can take away parts of that machine, fit them in, take away parts of the machine or fit things together, and everything is consistent. That's all these two axioms say. Okay. One more remark I need to make about this axiom is what happens when there are no internal disks, because that is an important case. We will use that often. So what if the tangle T tilde has no internal disks? Then what happens? I.e. T tilde has okay. So in this case, we need to modify this somewhat. So what modification is needed? This part, this part is going to be totally missing. There's going to be nothing here, right? Because there are no internal disks of T tilde, this part is going to be totally empty. So this is going to be an empty tensor product, and an empty tensor product, we will think of it as just scalars, the field C. So if T tilde has no internal disks, then we stipulate that the following diagram commutes. And it's very similar. So what is this diagram? You have k1 epsilon 1 up to I minus 1 and nothing, so you just have C here, or the field, whatever it is. Then you have up through KB epsilon B. And this is going to be Z of T circle. Oh, okay. Let me see, how do I do this? So what I want to do is, let me put it right. Okay, so this, by this isomorphism, the natural isomorphism, so this gets identified. So this, if you look at what are the internal disks of T circle T twiddle, there are these I minus 1 and those B minus I. These will be the, so this map makes sense here. So T circle T twiddle over Di, and it goes into Pk naught epsilon naught. I should have done it the other way. I should have written this one on top and that one at the bottom. And on the other hand, from here, let me put it like this. I have a map by identity on the first few. Then I have this map ZT twiddle, which goes from an empty tensor product to that outside one, and then identity on the rest, this rest of it. So where does this go? This goes into Pk1 epsilon 1, Pki minus 1 epsilon I minus 1. ZT twiddle, T twiddle has no internal disks, so the map goes just from scalars to whatever its outside color is, and its outside color is Ki epsilon I. We assume that. Pkb epsilon B. And this again is the list of all the internal disks of T in order. So here the map ZT makes sense. So it's just the same, almost the same, except you have to take a little care about, there's one additional isomorphism involved here, natural isomorphism. Again, yeah.
Both these things become necessary if you take the multilinear point of view you described earlier.
Which is?
That any ZT
Yeah.
is a multilinear map
From
the Cartesian product of these
internal. Yeah.
to the external thing.
True.
And then both these things, there is only one thing you can do.
But even here, this is the only possible thing you could do, right?
Yeah, but you don't have to spell the word separately. I'm saying you just, if you define it as,
if you define it as a multilinear map from the Cartesian product of the internal disks to the external disk space, then again you are saying we won't have to do two cases separately.
yeah.
Okay, so then how would,
If you take the T circle T twiddle,
yeah, it will have these, everything except the ith one. So that gives a map.
so you look at the two prescriptions that you have here. So on the one hand, you say you first I minus 1 thing.
Yeah.
And you take a scalar.
Yes.
You take a bunch of things.
Yes.
And then you get out a number.
True.
With a multilinear map, then by definition, that
Scalar can.
assume it is 1.
Yeah, but that's exactly, yeah, that's true. That's exactly what's being done here. True. Yeah. Okay. So, but I want to say a little more about this. I want to say a little more about this case actually, with one good reason. So what this is actually saying is the following. So the meaning. So I'll do this by an example. So take a tangle without internal disks. Let's say this tangle E2 plus. So E2 plus, we already named this, is this so-called Jones projection tangle, which looks like this. So no internal disks. This is E2 plus. Now, what does Z of E2 plus do? So Z of E2 plus, every tangle has a Z, and where does this go? It goes from the tensor product of the spaces associated with the internal disks. There are no internal disks. So it's an empty tensor product. So Z of E2 plus goes from C into the space associated with the external disk. The external disk is of color 2 plus. So it goes into P2 plus. So this any tangle with no internal disks always specifies a map from your field into the appropriate outer disk space. What this compatibility says is the following. So now let's consider denote by E lower 2 plus the element ZE2 plus of 1, which is an element of P2 plus. Now take any tangle S which has an internal box of color 2 plus. So if S is any tangle with say ith box of color 2 plus, then S circle di E2 plus makes sense. So what this thing is saying is, how do I say? Okay, so then the compatibility says then says the following. So you could take Z of S circle di E2 plus. So this is a tangle, and what are its internal disks? Its internal disks are the first I minus 1 of S and the last B minus I of S. So you could apply this to x1 tensor xi minus 1 tensor xi plus 1 up to xb. So this compatibility says that this exactly equals Zs applied to x1 tensor xi minus 1 tensor this element E2 plus tensor xi plus 1 tensor xb. If you look at the commutativity of the diagram, that's exactly what it says. What this means is, Thus, the picture has a meaning in every planar algebra P. As what? It has a meaning as this element. But we don't really have to keep track of this. What this means is whenever you can actually use this picture to stand for this element. And this we will do often sort of unconsciously. And it will take a little bit of time to understand. I have still not explained it, I think, well enough. But basically what I am trying to say is this picture in any planar algebra stands for this element. So whenever you have to use this element, that is this E2 plus, you can just substitute that picture. That's what the compatibility with substitution says. Okay. So that's two axioms, and then there's the third, which is relatively easy. So third axiom is the non-degeneracy axiom. So for this, let me recall that we defined a tangle called the identity tangle. For every color k epsilon, we defined the identity tangle of k epsilon. So recall the identity tangle of k epsilon. This was an annular tangle, the first example of an annular tangle we gave. So which looks like this. Suppose k epsilon is 3 minus, it looks like this. This is the identity tangle of color, single internal disk of color 3 minus, external disk also of color 3 minus. So that is the identity tangle of color 3 minus. And the axioms of a planar algebra say that the data, something wrong?
Suppose P2 plus is 0 for some planar.
P2 plus is 0, then everything is 0. There is nothing at all. Everything is 0. Yeah. Because it has an identity. P2 plus, we know, we are going to show it has an identity element. If it has only 0, then 1 and 0 are the same. So that means the whole thing is trivial. Now why did you ask that in this thing?
Because E2 plus
Yeah,
is 0.
E2 plus will be 0.
That means that every ZS must be 0.
Everything will be 0. True. Yeah, every ZS.
And so with non-degeneracy, that means that everything is 0.
Everything is 0. Yeah. Okay. So non-degeneracy, we begin with this identity tangle, and this identity tangle for any planar algebra is supposed to give you a map. So this gives. So let's temporarily call this just I, the tangle I. So this gives Zi for the planar algebra P, which will go from P3 minus to P3 minus. And non-degeneracy says this map must be the identity map. So we impose the condition that the axiom is that Z of ZPI is the identity map of P3 minus, and not just for 3 minus, for any color k, right? Any color k epsilon. Every identity tangle of color k epsilon gives you the identity map of that vector space. I am just thinking how could it, I am just wondering how could it not, because, oh I see, yeah, oh right, because we do not know it's spanned by the ranges. Right, right. Yeah, 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 true. Yeah. Yeah. So this, it can be shown that this is equal. I don't want to do this right now, but it can be shown that this is equivalent to each pk epsilon is the span of the ranges of all zt's where t has color k epsilon. I won't need this. An exercise, okay. Yeah. Right. This non-degeneracy is equivalent to this. So now we have completely defined what a planar algebra is. A planar algebra is a collection of vector spaces indexed by colors. There's one vector space pk epsilon for every color k epsilon, along with maps zt defined for every planar tangle. These maps zt have to have the specified domains and ranges, as I said earlier. And the collection of maps is to satisfy the three conditions of compatibility with substitution, compatibility with renumbering, and this non-degeneracy axiom. Okay. So let's see if I can give an I don't think I can give an example yet. Yeah, non-degeneracy says, oh, you're asking why it is called non-degeneracy. No, this says that this is actually, see what could happen in a planar algebra is this gives a map from 3 minus to 3 minus. It could happen that this map is not the just given the rest of the axioms. It could very well happen that this map is not the identity map between P3 minus and P3 minus. It could be a projection. In general, it could happen, but we want that projection to be the whole thing. We want it to be identity. There's no, this projection has no kernel. That's all we are saying. So that's just for the name explanation for why it's called non-degenerate. Okay, so let me now define what is a morphism of planar algebras. So we have defined the object, now we define the morphisms between two such objects. So let P and Q both be planar algebras. So what is a morphism? So if PQ are planar algebras, a morphism from P to Q is what you would expect it is. So what is P? P is a collection of vector spaces indexed by color. Q is also a collection of vector spaces indexed by color. So you must have a map of vector spaces. For every color, you must have a map of vector spaces. So is a collection phi k epsilon going from pk epsilon to qk epsilon of linear maps. And the structure on the planar algebra is everything is specified by tangles, so it better commute with the tangle action such that this collection commutes with the tangle action in the following sense. Commutes with the action by tangles, in the sense that, So, if T is a tangle as usual, K naught epsilon naught outside and K1 epsilon 1, KB epsilon B inside. Then there are two ways you could go from P of the insides to Q of the outside. So, you could take Pk1 epsilon 1, Pkb epsilon B to Qk0 epsilon 0. You could go in two ways. One is you could first apply Zt in P, then you would land up in Pk naught epsilon naught. Then you could apply the phi of K naught epsilon naught to end up in Qk naught epsilon naught. That's one way. The other way you could do is you could apply a tensor product of all these phis. So, phi K1 epsilon 1 tensor dot 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 phi Kb epsilon B. Then you would land up in Qk1 epsilon 1 up to Qkb epsilon B. Then you could apply Zt, now applied in the planar algebra Q. So, this diagram is to commute. So, then this the diagram commutes. That is to commute for every tangle T. So, it is just a collection of vector space maps which commutes with the action of tangles. So, that is a morphism of planar algebras. Okay. So, even now okay. So, let me I still have to give an example. I'm not sure how to do it yet. So, what I'll do is I'll prove the first proposition about planar algebras. Or yeah. So, let me state that proposition first.
One question. I was just thinking. When you were defining the thing itself, that the planar algebra itself, you think of the Pk epsilons as the objects.
Okay.
And the Zts as the morphisms.
But
so, if I think of each planar algebra itself as a category.
Yeah, but the objects are not the Pk epsilons, right? Because you could have, I mean, tensor product of 2 is also an object in some sense. If I have 2.
Category.
Yeah, as generated by those. Yeah. Yeah, it can be.
Then what you're calling a morphism of category
will be a two category.
Mapping between two categories.
Tensor category morph.
Natural, what is the?
No, this will then be a morphism of tensor categories. If you want to regard it as a tensor category, then this will be a morphism of tensor categories, except I'm not quite sure about, yeah, I guess your original category you could just take to be, I don't know, I'm not, you must take a collection of circles to be objects. And your morphisms you are only defining from a collection of circles to a single circle. You are not defining, the morphisms are being defined in a very restricted fashion somehow. See, if you have the multiplication tangle, you have these two as input and that as output. But you don't have any morphism between two of these and two of those.
Composition doesn't make sense.
It is, I mean, that's what we could make some sense of it by taking stars and all that, but it's not clear how, I mean, it's not very easy, I think. Okay. So, the first proposition is the following. So, let P be a planar algebra. Then, for every color k epsilon, the vector space Pk epsilon has the natural structure of an unital associative algebra. With multiplication being specified by the multiplication tangle, with multiplication specified by the k epsilon multiplication tangle and unit given by z u k epsilon of 1, where we have already defined u k epsilon equals the unit k epsilon tangle. Further, P0 plus minus are also commutative algebras for the same multiplication. And finally, the inclusion tangles I k epsilon to k plus 1 epsilon, which also I defined earlier, give unital algebra homomorphisms. Of course, from pk epsilon to pk plus 1 epsilon. Okay. So this, one should regard this proposition as something like saying, when you start group theory, you show that identity is unique, inverses are unique. It's like that. It's like that proposition. So it will. It's very simple, but it will be initially confusing to do. So I want to do parts of this at least carefully. I'll leave out some parts. I'll do some. Because some of these parts, I mean, everything finally will come down to those axioms. So it's how you use those axioms. So what is being said here? So what we want to first show is that if you take a planar algebra P, which is a collection of vector spaces, then you take one color, k epsilon, and take the vector space of that color, pk epsilon. This pk epsilon, we want to say, is naturally an associative algebra, and this algebra structure, that is the multiplication and unit, are specified by certain tangles. The multiplication is given by the multiplication tangle of color k epsilon, and the unit by the unit tangle of k epsilon. So first recall. So let me just do an example. Say k epsilon is 3 minus. The proof is the same for everything. I'll just do the 3 minus case. So what is the multiplication tangle of 3 minus? So M is this tangle, external of color 3 minus, two internals of color 3 minus joined like so. And U 3 minus, I'll just call it U, is this tangle. So that's the multiplication tangle, and this is the unit tangle of color 3 minus. So what does what do the axioms of a planar algebra give? So we have therefore Zm. Where does Zm go from? So I should label the disks D1 and D2. So Zm goes from P3 minus for this disk, tensor P3 minus for that disk, into P3 minus for this outside disk. So it goes from P3 minus tensor P3 minus to P3 minus is a linear map, or a bilinear map from just the product of these two into here, equivalently a linear map from the tensor product to this. So, we have Zm here, and we also have Zu. Zu has no internal disk, so it goes from just the complex numbers to the color P of this external one, which is also P3 minus. So, we have these two things. We want to verify that something makes it an associative algebra. So, that multiplication specifies a bilinear map on P3 minus cross P3 minus to P3 minus, and we will take that as multiplication. So, how do we know that multiplication is associative? So, if Zm is taken to define multiplication on P3 minus, why is this multiplication associative? And here is where this substitution and all these axioms will come in. So, what I want to do is, I want to take this M, and inside the first disk of M, I want to substitute M again. So, let us consider the following two tangles. So, observe that following two tangles are equal. What are these two tangles? M circle D1M and M circle D2M. I want to say that these two tangles are exactly the same. How do I check that? So, what is M circle D1M? So, I begin with this M. Into the D1 disk of M, I need to substitute this second M. And what does that look like? And then I erase this outside, so this is no longer there. This is M circle D1M, and the way that's what. The way the disks are numbered is, since I am substituting in the first disk, this will get number D1, this will get number D2, and this one, which was the original D2 of this M, becomes now D3. So, this is M circle D1M. On the other hand, what is M circle D2M? Here is M. In the second disk of M, I must substitute this M. So, which again looks like this. And then this gets erased along with that star, all of that. This star also, I mean not this star goes away here, this star goes away there. After substituting, I get this, but now I am substituting this M into the second disk of M. So, the first one is still numbered D1, and the other two are numbered in order as D2 and D3. Now, if you look at these two pictures, they are identical, right? You can certainly make this go over there, or however you want to put it. It's D1, D2, D3 connected by 3 strands throughout. Here also D1, D2, D3 connected with 3 strands throughout. So, these two tangles are equal, and so by the axioms of a planar algebra, the Z of this and the Z of that are equal, because we said that it only depends on the tangle, right? It's not how it looks, it's in the same isotopic class, or whatever, however you want to put it. Thus, Z of M circle D1M equals z of m circle D2m. Okay. Now what I want to do is, I want to apply this on some elements. What I want to do is to show that Zm is associative, right. So let us apply this. So both of these are tangles with 3 internal boxes, right. Both of these are tangles with 3 internal boxes, disks of color 3 minus. So consider Zm circle D1m applied to X tensor Y tensor Z. What is this equal to? The substitution axiom says, so what I'm trying to do is I want to put in X here, Y here and Z here and see what the answer is. The substitution axiom says that it's the same as applying this M to the result of applying this M to X and Y and Z in the other box. So this is equal to Z M of Zm of X tensor Y tensor Z by the substitution axiom. That's on one hand. Let me consider the other one. Similarly, Z m circle D2m of X tensor Y tensor Z. What is that equal to? So in this one, I want to substitute X, Y and Z, but I could have, the substitution axiom says if I first substitute Y and Z in this and get this result, and then I substitute that result into the second box of this outside M with the first box still being called X, that result is the same as this. So this says Zm of X tensor Zm of Y tensor Z. But as I said, these two tangles, the pictures are the same. That's the final, the punchline is the pictures are the same, so these maps are the same. Therefore, Zm of X tensor Y tensor Z equals Zm of X tensor Zm of Y tensor Z. In other words, Zm is associative. That's exactly what associativity means. So this multiplication that we have defined on P3 minus, therefore, is an associative multiplication by the substitution axiom. Then we want to use the other thing. We want to say that this is a unit. So to show that P3 minus is unital, yeah.
The multilinear mapping point of view makes it much more transparent.
That it's associative.
These both define X into Y into Z.
Yeah, true.
And that defines X into 1.
Yes. I guess I'm not following. You're saying this proof is not needed, is it? Are you saying this is?
Yeah, it is supposed to define a multilinear map.
Yeah.
And
That's
both
fine.
of them define the same map by
They define the same map, but how do you know that? The point of this is to show that this defines the map xy times z, and this defines the map x times yz. That's where the substitution axiom is being used.
But if I think of this tangle as defining a multilinear map,
Yeah.
from P3 cross P3 cross
P3 to P3.
to P3, where does it send X comma Y comma Z? It sends this into
Something.
Y into Z.
Why? That's
Because that is how
if this thing was not there, if you just considered this tangle, there will be just this outside and these three things connected by 3 lines throughout. You're going to put x, y and z in each. So it sends it into some multilinear function of x, y and z.
no, but by definition it is the
Yeah, I agree. That's fine.
And so when you do that thing, it will be xyz going to xy into z.
Why xy into z?
Because then there is one.
This picture is not there. You are only beginning. You only have this picture. So you base your argument on this picture. I put x, y, and z here. Now tell me. Unless you appeal to the substitution, how will you do it?
Only through substitution you're able to go from the earlier formulation to this multilinear formulation. That this doesn't depend on which order you clump those things.
No, that has nothing to do with substitution. That's completely independent. The multilinear formulation and this as a map from tensor product into this thing are completely equivalent. That has without any axiom at all. You still have to. I don't think. See, all you are saying is to say that a map from P2 tensor P2 into P2 is equivalent to saying bilinear map from P2 cross P2 to P2. These two are equivalent anyway with no axiom. So substitution is not used there.
So, but if these two tangles are the same, they will define the same multilinear map.
That's correct. Yeah, that's true. That is true. So there's only one multilinear map which both of these define, which is x y z goes to x y z. That's the map. But only by substitution you can say that this defines the map x y z, whereas that defines the map x y z, and therefore these two are equal. So, but substitution you can't avoid anyway. The multilinear viewpoint doesn't take away that. You still you still have to. Okay. Now we want to show that this is a unit. So you want to show that this is unital with unit given by whatever zu of 1. Okay, again we'll begin with a tangle and do something and derive this. So as I said, okay, so let's see. So consider the tangle M circle D1 of U. U is a 3 minus tangle. M has two internal disks of color 3 minus. So I can substitute. This makes sense. M circle D1 of U. Let's just see what it is. It's just a pictorial calculation. That's the main advantage of planar algebras is all kinds of algebraic calculations will just come down to verifying various pictorial identities. So M circle D1 of U looks like this. You begin with the multiplication tangle. That's this. And then into the first disk, into D1, you substitute the unit tangle. And that unit tangle just looked like 3 lines. This was the unit tangle. Then you delete this outside thing here. So what you get is this new tangle here. And that of course is not a new tangle. That's, of course, we know what it is. It's the identity tangle. So this is just I. M circle D1 of U is just I. The identity tangle of color, in this case, I'm only doing 3 minus. It's just I of 3 minus. Now we will use the the axiom of degeneracy. Zi is just the identity. So Z of M circle D1U is Zi is the identity map of P3 minus. On the other hand, compatibility with substitution says that Z M circle U of D1, this is by compatibility with substitution when b tilde is 0. That's why I did this case separately. So the case for compatibility with substitution when b tilde is 0 says that this is equal to Zm of whatever, this first one, Zu of 1 tensor dot. So Zm has two inputs. It says compatibility with substitution says you just substitute that one into the first box and whatever is left in the second box. So what this says is, if you call this element whatever, little u say, right. So Zm of u tensor x equals id applied to x is just x. But Zm of u tensor x is what you are defining as ux. So ux equals x. So that says that u is a whatever one-sided identity. And similarly, by substituting into the second one, you will see that it's the other-sided identity. Similarly, M circle D2 of u is also equal to the identity map, which implies that Zu of 1, which I call little u, is a right identity. So we have checked that u is both left and right identity. Okay. So we have verified that all the pk's are pk pluses or pk minus pk epsilons are unital associative algebras, and part of the assertion also was that p0 plus minus are commutative algebras, and this really uses the isotopy invariance. So to show that p0 plus or minus are commutative, so consider m0 plus minus. Let's consider this multiplication of 0 plus. The multiplication of 0 plus is the following tangle. I have drawn this earlier. So it has an external disk of color 0 plus, two internal disks of color 0 plus, one called D1 and one called D2. And there is only one possible star region, which is colored white. So this is the multiplication tangle of 0 plus. And we already observed before that if I do sigma of m, where sigma is the permutation 1, 2, is equal to m as a tangle. That is, sigma of m is the same one with 1 and 2 interchanged, but then I can rotate it, and that's a orientation preserving diffeomorphism of R2, and then get it equal to m. So sigma of m, whether I have 1, 2 here or 2, 1 there, it's the same tangle. So there's only one tangle. So, but multiplication in P0 plus is defined by Zm. That's the definition. That's how we define. And so by the renumbering, axiom, for no.
That if you take any mk,
yeah,
and if you look at the non-trivial,
oh, with op,
then you get the opposite.
yeah. I actually, maybe that. Yeah, I should say that. I'll say that. Just 1 second. Let me finish this, and then I'll say the general one. So by the renumbering axiom, Z12m of x tensor y is Zm of x tensor y, which by definition is xy. On the other hand, Z12 of m is also what? Yeah, is Zm of y tensor x, because I'm applying the permutation 1, 2. So this is yx. So yx equals xy you get. And then as Sundar says more generally, this is what one should have said. So more generally, for any k epsilon, consider M, the multiplication of type k epsilon, and sigma M, where sigma is 1, 2. So consider the two tangle, multiplication tangle and the multiplication tangle with the disks numbered the other way, M and sigma M. So renumbering will say, renumbering compatibility says that Zm of extensor y is Z sigma M of y tensor x. So I'll just draw this quickly and explain once more, because this is the kind of arguments which will be used often. D1, D2, and here you have some things. This is D2, D1. So this is sigma of M, and this is M. So renumbering compatibility, if I put x here and y here, that's the same as putting x here and y here. That's what renumbering compatibility says. The inputs, the output depends only on where you put the inputs. It doesn't depend on how you labeled these things. So if I put x here and y here, it's the same as putting y here and x here. Putting y here and x here means Z sigma M of x, y. That's this side. And putting x here and y here means Zm of xy. So these two are equal. That's exactly what renumbering compatibility says. Okay. So this applied to the case of 0 plus will say that Zm of extensor y, but in this 0 case, the additional special thing that happens is sigma M and M are equal by rotation, which is not the case when, even if I rotate this, there is no way, I mean I don't know how to prove that, but there is no way I can make this and this coincide by a diffeomorphism of R2. Well, I guess we can prove it by a diffeomorphism which preserves the star regions, which preserves these mark points, which takes these mark points to those mark points, because the mark point which is immediately adjacent to the star region here is connected to something in D1, whereas the mark point which is immediately adjacent to the star region here is connected to something in D2. This cannot be altered by a diffeomorphism. So you will not have a orientation preserving diffeomorphism of R2 which will take this to that one. On the other hand, you will have an orientation reversing diffeomorphism of R2 which takes this there. We will come to that later. Okay. So I guess I have proved. Yeah, one more thing was there, that I will leave as exercise. So the last thing to be done was to show that if I take an inclusion tangle, something like this is the inclusion tangle from say 2 plus to 3 plus. So this is I from 2 plus, internal box of color 2 plus to external of color 3 plus. This is supposed to specify a map from P2 plus to P3 plus. The axioms of a planar algebra say that such a tangle will give you a map from P2 plus to P3 plus. Now we made P2 plus into an algebra using the multiplication tangle. We made P3 plus into an algebra using its multiplication tangle. Then the proposition asserts that this mapping is then a unital homomorphism of algebras. So I'll leave it to you to check that last part. Okay. Okay, maybe I'll stop here. I'll continue. I'll continue. Friday is fine. Sundar. Is Friday okay? Friday, we'll have Friday at 11:30.